I'm going to be walking you through the types of chemical reactions and showing you how to use them. And so you're going to need your periodic table by you handy if you have it. The first type of reaction that I'm going to show you is called a synthesis reaction. And the general equation for a synthesis reaction is A plus B produces AB. Synthesis because you're taking two things and you're combining them together. A classic example of a synthesis reaction would be the combustion of magnesium. So you would take, so here's my example, take magnesium, which is a alkaline earth metal. When it's by itself, it's solid, and you add that to oxygen. If you look over here, oxygen is a gas and it's on the diatomic list. So when I write oxygen, I'm really going to write O2, and I know that it's a gas. So I'm going to take oxygen, which is a gas, and combine them together. So the thing when you combine elements together is that you have to remember that when you take two things and put them together, they actually sometimes form ionic compounds. So in this situation, an ionic compound forms. So off to the side, I'm going to say that magnesium, when it combines with oxygen, is going to take on a +2 charge because it's going to give away 2 electrons. And then oxygen is going to take on a -2 charge. So off to the side, I'm just going to do a quick little cation, anion to form a compound. So it's a +2 -2, so it's a 1-to-1 ratio. So it forms magnesium oxide. So solid magnesium combines with gaseous diatomic oxygen to form solid magnesium oxide. So here's the thing. Because oxygen is diatomic, there's actually 2 oxygen atoms here, but I only ended up with 1 oxygen atom on the product side because magnesium and oxygen had cation-anion cancellation. And so that's why I would have to balance this equation. Balancing equations, remember, using coefficients, go on the lines in front to show that, yes, in fact, what I put in, I get out. So if I put in 2 oxygens, I need to get out 2 oxygens. So I'm going to put a 2 coefficient in front of magnesium oxide, which tells me that I got 2 oxygens out. However, this now tells me that I have 2 magnesiums as well, so I'm going to go back and put a 2 in front of magnesium. So really what this shows is that I took 2 atoms of magnesium, combined it with 1 diatomic oxygen molecule, and produced 2 magnesium oxide compounds. So that's a synthesis reaction. A plus BC equals AB. Decomposition reactions are the exact opposite. A decomposition reaction is when you take that AB and it falls back apart into A plus B. So if I were to write this, I could write the exact opposite of this equation. So I, just as an example, keep it simple, I could take magnesium oxide and then it would fall back apart into magnesium and diatomic oxygen, like that. So you just write it backwards. The next type is a single replacement reaction, which we have already talked about, but I'll just add it to the list so that you know that we are going to be using them again. A single replacement reaction is when you take solid A plus BC, which is aqueous, and it forms AC, aqueous, plus B as a solid, like that. So these states of matter are pretty set in a single replacement reaction. You notice how on A plus B equals AB on the synthesis and the decomposition, I did not include states of matter. That's because we need to be a little bit more flexible on those with the states of matter, but on this one it's pretty steady. And so on this one you would use the activity series if you're dealing with metals particularly. It's not always going to deal with metals, but for this let's talk about the activity series. So let's say that I have a solid piece of lithium just as my example, and I add it to something that's lower, let's say iron 3 chloride as an aqueous solution. It's going to produce lithium chloride. as an aqueous solution, and iron is going to get left alone like that. And the reason why lithium and chlorine, there's only one chlorine here versus 3 chlorines here, is because here I had Fe plus 3 plus Cl minus 1, and that would be a 3 chlorine for 1 iron ratio. And over here, lithium takes on a +1 charge, chlorine is a -1, therefore it's a 1-to-1 ratio. So you have to watch your charges when you're creating the ionic compounds. So because I have 3 chlorines on the reactant side, I'm going to need to put a 3 over here to distribute to this chlorine, but I now have 3 lithium, so I'm going to come back over to my reactant side and put a 3 on the lithium, so now I have a balanced single replacement reaction. The last type of reaction that we're going to be dealing with is the double replacement reaction, and we're already a little familiar with these from our last unit. So the double replacement reaction, AB plus CD produces AD plus CB. And so let's say that we have sodium hydroxide. AB is always aqueous. CD is always aqueous. And we add that to aluminum chloride. It's going to produce a precipitate, which is solid, and an aqueous solution. So let's figure out what's what. So if sodium is A and chlorine is D, sodium takes on a +1 charge as a cation, chlorine takes on a -1 charge as an anion, so it forms NaCl. So that would be this one and this one. And the second compound is going to be aluminum, which combines with hydroxide. So aluminum has a +3 charge, hydroxide has a -1 charge, it's a polyatomic ion. I'm going to need 3 hydroxides for every 1 aluminum. So then you look at your solubility chart to determine which one is which. So I see hydroxide right here. It says hydroxide plus an alkali ion. It's kind of hard to see with the plastic. Or ammonium is soluble, but any other positive ion is going to be insoluble. Well, aluminum falls into the any other positive ion. Therefore, this is going to be my solid, which means this is going to be my aqueous. So AD is going to be, put lines there, aluminum hydroxide as a precipitate, and then sodium chloride as aqueous. So that's my CB. And now I need a balance. So because I have 3 hydroxides on my product side, I'm going to come over here and put a 3 in front of sodium hydroxide because I now have 3 hydroxides. I now have 3 sodium, so I'll come back over here and put a 3 in front of my sodium, which makes sense because I now have 3 chlorines, but I needed 3 chlorines anyway. So this would be a balanced double replacement reaction using the solubility chart. So those are the 4 different types of reactions that we're going to be working with for the next couple of weeks.